Hey everybody, we are back for day 2 of talking about electrons and where they hang out in the atom. And today what we're going to be talking about is kind of the more specific locations of each of those electrons and giving them an address, which is what we call electron configuration. So the PES diagrams that we looked at yesterday help confirm the locations of the electrons within the structure of the atom. And what it does is it kind of helps us put a definite location on where we can find the electrons most of the time when we look at an atom. And what's important about that is, like I said, it gives us hints about how an element is going to bond together. And specifically, the outside electrons or valence electrons give us that information. And so what we're going to be talking about today is the electron configuration or the address for an element. And so it is giving the address for each of the electrons within your element. Now, at any given point in time, you can't poke your finger and find an electron. But what happens is if we know where most of our electrons sit and we call it our electron configuration, we know where the electrons are hanging out in an atom about 90 to 95% of the time. And so those configurations just give us more information to work with. Now, an electron configuration is always kind of set up the same way. So what I've done is I've included the electron configuration for helium here as the example, and then we're going to go through all of the examples we did yesterday and show you how to write the electron configurations for them. And I'm going to show you kind of a neat little trick we can do and use our periodic table for. So if you look at the electron configuration for helium, it is 1s2. And the 1 in the 1s2 represents the energy level. Now that is basically the shell and its distance away from the nucleus. So if I have electrons in the 1 energy level or the first energy level, it means that they are closest to the nucleus. Second means they're further out. And you can get all the way to the 7th shell or the 7th energy level when we talk about these. So in an electron configuration, in theory, you could see an electron configuration go all the way to starting with a 7. Okay? And electron configurations grow larger the more electrons you have. Helium only has 2 electrons, so it's pretty small, but they can get pretty big and kind of annoying. The S represents the subshell where those electrons hang out. And we talked last time about the 4 subshells that we see. The S subshell, which can hold a maximum of 2 electrons, the P subshell, which can hold 6, the D subshell that can hold 10, and the F subshell that can hold 14. So make sure that you keep those in mind. Those are really the only subshells that have electrons in them for the elements that we know, and so those are the ones that we're going to use. And then the little 2 that is in the form we call a superscript form, super means above, so it's in the superscript, tells us how many electrons are in that subshell. So for the case of helium, we have the 1s subshell, and there are 2 electrons that hang out in there. Okay, so we are going to be kind of going over a bunch of different examples, and hopefully we can get things cleared up and hopefully things make sense to you. So here's my handy dandy periodic table, but you may notice that I don't have any element symbols here. So what I did is that before I got to talking to you guys, I went through and I looked at all of the different examples that we went through yesterday, including the example problems that were separate from the lecture. So there should be 6 total ones that we went through. And what I did was I counted up the subshell electrons and wrote them in their position on the periodic table. So you will see here, I've got a 2 and a 1 for lithium in lithium's box because lithium has 2 electrons in its first subshell and 1 electron in its second subshell. So that's why I wrote it like that. Okay, so all I did was I went through all of these and wrote them down. So 2, 2, and 1 goes into the box for boron. 2, 2, 4 goes into the box for oxygen. And then these guys here were the examples from the understanding checks as well, the practice understanding checks. So all I did was kind of fill in all of these values for the examples as well as the practice and the understanding check values. So there are a bunch of numbers in here. Okay, so when we take a look and we want to write an electron configuration, these numbers in the subshells are really important. And what we need to be able to do is write down their electron configuration. So I'm going to show you what lithium's is, and then I'm going to show you a shortcut on how to figure that out. So if we look at the subshells for lithium, lithium's first subshell had 2 electrons in it, and then its second one had 1 in it. Now, the way that electrons fill in an element, if I go back to lithium's picture here, is that they fill into the subshell closest to the nucleus first, and then when there's no room in that shell, they go to the next subshell. When that one is full of electrons, they go to the next subshell, and so on and so forth until we run out of electrons to put in those shells. And so when we fill out our electron configuration, what we do is we notice some patterns. Now, if you notice in lithium, and basically everything in all of our elements that we looked at, the first subshell, which is represented here, only holds 2 electrons. And the subshell that holds 2 electrons is our S subshell. So the S subshell holds 2. Again, P is 6, D is 10, and F is 14 electrons. So what happens is, I'm hoping you can kind of pick up the pattern, is that this first subshell that shows up for all of them must be an S shell. And the name for that very first S shell, it's very creative, is the 1s shell. Okay? Now, how many electrons are in that shell? There are 2 of them. So I'm going to write 1s2. All right? Now, after the 1s2 shell, or the 1s shell is filled up, so if you think about your electron structure for lithium, lithium has 3 protons in it. The first shell that we see is the 1s shell, and it fills up with 2 electrons. And there's no room for anything else, so we go to the next subshell. Now, the next subshell is called the 2s subshell. The 2s subshell, being an S-type subshell, can only hold 2 electrons. But in the case of lithium, there's only 1 electron. So that works out great. And it can hang out in that subshell, and it's done. So our second part of our electron configuration is written 2s1. So for our lithium's electron configuration, it is 1s2, 2s1. Okay? A way to double check and make sure that you have this correct is to check all of the superscript values and add them up. And then we have 3 electrons total, and that is how many lithium has. So we're good to go. Okay. So we're going to try borons again. Boron here. It's our next example. Based off the photoelectron spectroscopy diagram, we had 2 electrons in our first subshell, then 2, and then 1. Okay, so the first subshell that exists is the 1s subshell. That can hold 2 electrons. So when we're filling in the electron shells for boron, we're going to fill in the 1s subshell, which can hold 2 electrons. The next subshell is the 2s subshell, and S's can only hold 2 electrons. So we fill up the 2s subshell, the next layer to our atom, basically, but we still have electrons left. And so we need to take our last electron and fill it into an even higher subshell, further away from our nucleus. If you remember, when we looked at boron, the first subshell had 2, so that's where this 1s2 is coming from. This is the 2s2, and then the next subshell that we're talking about is going to be called the 2p shell. Now, we talked about how the p shell can hold a maximum of 6 electrons, but in the case of boron, there is only 1 that we have to worry about, okay? So what we're going to do is we're going to put 2p1 there, and it's going to tell us that in that p subshell, that's 1 little bit further out from the nucleus than the 2s shell, there's going to be just 1 electron in there, and so it matches up with our structure. Okay? We'll do another one for oxygen. Okay, so if you remember oxygen's diagram, our subshells went 2, 2, and 4. So my electron configuration is going to have a 2, a 2, and a 4 in it. And what we'll do is we'll write 1s2 because the 1s shell, again, is the closest subshell to the nucleus. It fills in, and then when we have no room in there because we've packed it full of 2 electrons, we move out to an additional shell, kind of like layers in an onion. So this is our first layer of our onion. Our second layer of the onion is the 2s shell. And the s shells, all of them, no matter what, can only hold 2 electrons. So we put 2 more electrons for oxygen in there. And then once that layer of the onion is full, we go and build another layer. And that third layer is the 2p shell. Now there are 4 electrons in the 2p shell. So I'm going to put 2p4, okay? It could hold 2 more electrons all the way to 2p6. And so if we had an element that had 2 more electrons, its electron configuration would be 2p6 at the end. So what happens is as our elements get bigger, their electron configurations get larger and larger and larger again. But now you say to yourself, Mrs. Ottmeyer, how in the world am I supposed to keep all these memorized? I don't know the order for all of these shells. So you told me it's the 1s, then the 2s, then the 2p, and that's great. But what does that actually mean when I have to do this? And I will tell you, I'm not going to give you this graph every time. And the reason why is because the periodic table is built to give you a hand with this. So what happens is, if you've ever paid attention to the periodic table, it has kind of this weird shape to it. Like, why is it weirdly high over here with 2 boxes and then weirdly high over here with 6 boxes, and then all of a sudden it's lower, and then there's these chunks at the bottom here? That is all honestly by design, and it helps us actually explain the electronic structure and the electron configuration for a lot of stuff. So what happens is on our periodic table, these areas are actually called blocks. So depending on the area you are in on the periodic table, it will be considered a different block, okay? So you may want to write this on your periodic table as we go along. Groups 1 and 2 on our periodic table are called the S block. And the reason they are called the S block is because the elements that sit in this group 1 or group 2 have electron configurations that end in an S. Okay? This block over here is 6 boxes wide. It is called the P block. And the reason it's called the P block is because elements that are over here, they have electron configurations that end in P. This middle section, that's kind of a little bit lower, that is called the D block. Okay. And then lastly, way down here at the bottom, this is called your F block. Now, the F block honestly gets a little complicated, and this year we are going to kind of ignore it because it makes life difficult, but just know that this is called the F block down here, okay? So all of these different types of blocks that we see will help us find our electron configuration. And the way that we figure that out is that we take a look at the period number, and that tells us the block. So this is the 1s block. This is the 2s block. This chunk over here on the right-hand side, that is the 2p block all the way over. 3s, this is 3p, and so on. Down here we have the 4s, and then we will talk about this stuff a little bit later. So right now we're just going to kind of focus on this chunk, and then tomorrow we'll focus on the rest of it, okay? So when we want to find an electron configuration, it's actually a lot easier than you think it is. So let's go back to oxygen here. Now, I already told you that oxygen's electron configuration is 1s2, 2s2, 2p4. So what I like to do when I like to write an electron configuration is I use the periodic table like a roadmap. Like, you know, on like a board game where you got to follow the same route every time. That's kind of how I think of electron configurations. So if I want to get to oxygen, which is here, I need to travel starting with the 1s block and then go through every block until I get to this box here. So I'm going to travel through the 1s block. And you may say to yourself, why is helium over here? Helium is a problem child, and this first period kind of doesn't follow the rules, but everything else does. So I'm going to travel through the 1s block. Then I start over and I travel through the 2s block. And to get to oxygen, I end in the 2p block. Now, do you say to yourself, okay, I kind of get where the 1s2 comes from because I traveled through 2 boxes in the 1s block. Then I traveled through 2 boxes in the 2s block. To get to oxygen, I have to travel through 1, 2, 3, 4 boxes in the 2p block. And that's where my electron configuration of 1s2, 2s2, 2p4 comes from. Okay, so what I want you to do is I want you to try 3 more examples and we will work them out together. So the first example is going to be aluminum. Okay, so aluminum we are going to find, and I'm going to get my other periodic table out. And if your periodic table doesn't have the numbers on them, feel free to write on it. So I'm going to put 1, 2, 3, 4 on my periodic table to make life easier. And if you want to write S block, P block, D block, you go for it. All right, we're going to find aluminum. So aluminum is down here and it's in the 3rd period. So that means that this is the 3p block, which means my electron configuration for aluminum is going to end in 3p. So I start here. I go through the 1s shell and I travel through both boxes. So I'm going to write 1s2. And what that means is that 2 of my electrons go in the 1s shell. So think about it as you're traveling along here, you are dropping electrons off in the shell. So bloop, bloop, 2 electrons into the 1s shell. Then as I pass through the 2s shell, I drop 2 electrons. So I'm going to write 2s2. I need to go all the way through this shell here. So I'm going all the way through the 2p shell and I travel through 1, 2, 3, 4, 5, 6 boxes. So it's going to be 2p6. Then I keep going. Now I'm in the 3rd period and I go through 2 boxes in the S block. So I'm going to write 3s2. And then I hit aluminum. Aluminum is the first box in the 3p subshell. So I'm going to write 3p1. Okay. So hopefully that makes a little bit of sense. There are 2 other examples that I'm going to have you guys go through in the other video. So please give those a try. And if you find that you're having any trouble, please make sure you're going to a Google Meet. With electron configuration, we tend to find that things are a little bit difficult until all of a sudden the light switch goes off. And so if the light switch hasn't gone off to you by the time we get through the examples and the sample understanding check, it's time to come to a Google Meet and we'll get things cleared up. Okay? Good luck on the examples and we will see you guys next time.